Welcome to Quantum Curious, and in today's video, I'm going to discuss a very important detection scheme, and it is usually referred to as phase-sensitive detection scheme. So in the previous lectures, we reviewed some concepts related to squeezing of the state of light, and we saw that using squeezing operation, we can reduce the fluctuations of one of the quadrature uh, in, below this the quantum limit, that is the vacuum limit. And in order to uh, satisfy the Heisenberg uncertainty relation, the fluctuations uh, increases in the conjugate quadrature. And so we know that squeezing is a phase-dependent phenomenon, and we cannot deduce it in experiments that are related to intensity measurement. On the other hand, we also know that phase is not a physical observable in quantum mechanics because it is not associated with any Hermitian operator. But we can deduce the phase of two states of light uh, using interference phenomena, and the phase can be measured indirectly, and the quantities that are phase dependent can also be measured and observed using interference like phenomena. So we are going to use these facts in order to uh, design a technique that can deduce and help us observe phase-dependent quantities. So let's move on to the introduction of today's video. So we know that squeezing is a phase-dependent phenomenon, as I have described earlier, and we cannot observe it using direct photon counting measures that usually associated with intensity measurement, and they are not for phase dependent. So squeezing cannot be detected using these kind of techniques. So we use phase sensitive interference. So in this interference phenomena, we have to use a reference beam that can be controlled. So one of the experimentally friendly state of light is a coherent state because it is a quasi-classical state, and we can control its phase and amplitude quite easily. So using intensity fluctuations, we can deduce phase-dependent properties, including squeezing. So let's move on to the technical details of the Homodyne detection scheme. So it is helpful in order to detect phase-dependent properties of the field, and we have two types of techniques. One is homodyne detection, and the other is heterodyne detection. So the difference between two techniques is that in homodyne detection, we can only measure one quadrature at a time, but in heterodyne detection, we can measure both quadratures simultaneously. But we know that both quadratures are bound by the Heisenberg limit. So the heterodyne detection is much noisy as compared to the homodyne detection. So this is a simple schematic of our experimental setup. So we need two fields. One is unknown signal field that we want to measure, and the other is the local oscillator. And it is usually a strong laser field that we can control. So after combining it using beam splitter with some transmittivity and some efficiency, we get a combined field. And we can detect it using photoelectric counting or photocurrent spectral measurements. So writing it in terms of, or in the language of quantum optics, we have two field operators representing the weak field and the local oscillator. And the beam splitter has some transmissivity data. So the field operators can be written in terms of creation and annihilation operator of the modes. And the combined accretion operator or annihilation operator can be written as this, where aorta is representing the phase gain by the reflected light. So the combined electric field operator can be written as this in terms of combined accretion and annihilation operators. So first, we will see that how can we deduce phase-dependent quantities using the measurement of the intensities. So we can measure the intensity by this kind of expression and plugging in the accretion and uh, annihilation form of the combined accretion and annihilation operator, we can get this kind of expression. So we know that our uh, signal field is quite weak and it is also unknown. So we are going to make some assumptions. So we know that our reference beam, that is a strong local oscillator, is quite strong. So we will ignore the terms that are not related to our strong local oscillator. So the first term is only related to the weak field. So we are going to ignore it and we will keep it because it is associated with our stronger local oscillator, and we will also keep this. So we are going to end up with this expression after making some assumptions. So the first term is related to intensity, and the second term is related to the interference term. So we can see that uh, this expectation value is related to the phase of the local oscillator. By changing the phase of the local oscillator, we can change this quantity, and you can see that it is somewhat giving some a sense of the expression of uh, the quadratures of the field. So changing the phase of the field of the local oscillator, we can get values or expectation values of the different quadratures of the given field. So using this technique, we can measure quite easily the phase-dependent quantities like quadratures uh, of the field or of the unknown field. Similarly, we can also observe the fluctuations by using the variance. So this term is again showing the local oscillator noise, and it is showing the interference terms between the weak signal and our local oscillator. So we know that it will give the fluctuations in the quadrature, and by changing the phase of the local oscillator, we can observe two different fluctuations or two different quadrature fluctuations. So here is a graphical representation, and we have plotted our uh, quadrature fluctuations against the phase of the local oscillator. So we can see that for some values of the phase, the fluctuations are quite high. But on the other hand, we can also see that for some values of the phase, we can see that the fluctuations are below the vacuum level. And we can see that it can only possible for the squeezing or the squeeze states of light. So we can see that by changing the phase, we can observe different phase dependent properties like squeezing of light. And we can also measure the quadratures. So here are some experimental cautions or instructions that we have to follow. We usually first deduce what is vacuum noise by locking our signal field. And after deducing how much vacuum noise we have, we can eliminate it from our results for the signal field, and we can get very clean results that are only uh, uh, dependent upon the phase of the local oscillator. And we have another homodyne detection technique called balanced homodyne detection scheme. So in which we have a beam splitter, and after getting two outputs from the beam splitter, we can detect the photocurrents on the two outputs of the beam splitter, and we can subtract the results of these two photodetectors, and we get an illuminated and clean quadrature fluctuations, and it is cleaned from the local oscillator noise. So we can get a very clean results using these kind of technique. So we have today discussed what is phase sensitive measurement and how can we do it. And we also saw that why the uh, why the techniques that are usually associated with the intensity measurements are not that much of helpful, because they do not have that kind of interference. And we also saw that how we can deduce it mathematically, because we have two terms. One is related to interference and one is related to intensity. So the interference term is going to play a very crucial role in order to uh, help us, in order to help us to observe the phenomena that are phase dependent.